Okay, welcome to class meeting 25 of EECE574, the graduate level probability and random processes. Last time, when I talked about the final exam dates, I made a serious mistakes. So it will be either taken half on Tuesday, June 6th. Is it holiday or what? That is strange. Just a second. Because I've seen some email that, okay, so this will not work. So probably I will reserve a classroom, possibly here or 102 or 104 on Wednesday, June 7th. Got it? So there are some undergraduate courses that are taken on June 7th, but I don't believe you are taking it, like Physics 101, something like that. Okay, so, okay, let's fix it. Okay, so we will take the final exam on Wednesday, June 7th from 7 to 10 p.m. here in LG Research Building. The specific classroom will be announced next time. Got it? Handout select notes are available from our primary homepage. And please tell me about your voluntary projects before you take the final exam. There will be homework assigned, actually homework assigned due just before, and there will be some other homeworks. Corrections, clarifications, I found none, and here goes the overview. So we are almost finishing this stochastic convergence and limit theorem section, and we are going to enter systems with stochastic inputs. And then we quickly cover power spectrum and other topics that was supposed to be covered in the beginning of this course. Let's review. So last time we studied some central limit theorems. Okay. And we've seen some examples of convergence in distribution. And here, this was related to the central limit theorem, and this was related to central limit theorem. But the Poisson approximation to a binomial random variable was not central limit theorem. It was just an example of a sequence of random variables converging to another random variable in distribution. So what happened to the camera? Is it gone again? Okay. So we have almost sure convergence, or with probability 1 convergence, and here convergence in the Pitts mean for p greater than or equal to 1, and they both imply convergence in distribution or in measure, in probability or in measure. And they all imply convergence in distribution. And last time, at the end of the meeting, I emphasized that in most of the applications, you want to prove this because we handle probability in many cases, not all. So, for example, here in the calculation or approximation of bit error rate of a synchronous direct sequence spread spectrum multiple access, or simply DSC-DMA system with random sequences, the multiple access interference is simply a binomial distribution properly scaled and shifted. And as we've already seen in one of the central limit theorem, that random variable converges in distribution to a Gaussian random variable. So we know that the multiple access interference for sufficiently large processing gain or spreading gain, its distribution is very close to a Gaussian. Then what was the bit error rate we wanted to show? Bit error rate was defined as what? The probability of event that your estimate is not the true value when b equals 0, and probability of the prior probability plus your transmitted bit and estimate is different when the transmitted bit is 1. So this is your average probability of bit error. If we assume the prior probabilities are the same, it can be just written as this one. And you know that after some assumption about our receiver, this is same as your observation is, for example, if you map, this to b equals 0 to some, okay, I'd better not use that. Let me use -1 and +1. That's straightforward. Okay. So let me use -1, +1. In that case, -1. So something like this. So here, even though you transmitted b equals -1, that value is corrupted by the multiple access interference, which is well approximated as Gaussian, and also corrupted by a Gaussian random variable. So you have some distribution density function like that. And we want to compute the right tail probability. And we know that this distribution is well approximated as a Gaussian distribution. So here goes the approximation, Q of something. Got it? So if you are interested in computing the bit error rate, packet error rates, and sum error rate, in many cases, you are interested in the approximate CDF of something. And to prove that is close to, for example, Gaussian, or sometimes Poisson, you just need to prove convergence in distribution. So when I was a graduate student, there was some trend in PhD thesis. They wanted to prove their analyzed performance is well parameterized by some specific important variables, and also that distribution is very simple, Gaussian, Poisson, or something. So many of us at that time, as a graduate student, took the analysis courses, real analysis, measure theory, measure theoretic probability courses, because we wanted to prove something, convergence in distribution, convergence in probability, something like that. And even though, what I found is this, even though my classmate just needed convergence in distribution, sometimes he or she proved a stronger convergence. Anyway, that implied this. Sometimes using the convergence in the piecemeal was easier for him or her, so they proved this one, but eventually they needed this convergence. Of course, there are some cases where you specifically need almost sure convergence or improbability convergence. Okay. Let's preview what you are going to do. So first, I'm going to talk about Monte Carlo integration and simulation very quickly, and then move to the Borel-Cantalli lemma, which I'm not going to prove, and I will just give you some example where you use Borel-Cantalli lemma to prove a convergence with probability 1, almost sure convergence. As I told you probably last class meeting, almost sure convergence sometimes is not easy. However, this Borel-Cantalli lemma makes the proof very simple. You just say that, okay, Borel-Cantalli lemma can be applied to my situation. Something is replaced by that, some other thing replaced by this. And then I can apply Borel-Cantalli lemma. I have almost sure convergence, something like that. And I will quickly summarize all the stochastic convergence and limit theorems, and then we'll move to stochastic calculus. Got it? before I talk about the Borel-Cantalli lemma, we need some strange notations or to some of you, familiar notations like this. First, we have, this could be understood as a set or event. And here you have a sequence of sets or events. And what would be this? It's similar to the sigma notation for the summation. So you have union of A sub I. These are subsets of some common set or universal set that is reserved for some other meaning. But anyway, so I runs from 1 to n, and you write AI. By the way, this is what? This is a notation, okay? This is a notation. This is not a definition. And the true definition is this one. So you have A1 union, A2 union, dot, 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 up to union A sub n. By the way, set union operator is actually has two inputs. So there is something wrong here. What is wrong? You must need some parentheses, for example, like this. Right? So you have A1 union A2, union A3, union A4. You have something like this, right? But why I didn't put parentheses? Because union operator can be what? Union operator has commutativity and what? Associativity, right? So it doesn't matter. And also, you have this notation that is called finite intersection. So this is finite union, or sometimes countable union, but I really hate. So finite union and finite intersection of events in probability case or subsets. So you intersect n of them. Due to the same reason, you don't need parentheses, even though intersection operator, set operator, accepts two inputs and generates one, because any possible ordering give you the same result. Because we can rewrite this one as a set of, for example, x, such that x is a member of AI for some I in 1, 2, dot, 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 n. Okay. So if x is a member of this set, the finite union of A1 to AN, then there exists some index I such that x is a member of AI, right? So here kicks in suddenly, there exists statement when you consider set union, especially finite union. And this one can be similarly rewritten as the set of x such that x is in AI for all I. So if x is a member of this finite intersection of subsets, then an element of this set must be a member of every subset, right? So this part is very interesting. Right? This is exactly the notation you've seen in the mathematical analysis. There exists for all, something like that. Right? Now, given these two, you may say that, well, it's just equivalent things. You're right. But given this, you have a very simple idea. However, we rewrite or we write it in this way allows us to extend it to what? Here, countable union and countable intersection. Here, some people say countably infinite union, countably infinite intersection. What's the difference between this finite union and countable union? What's the difference? Here you have countably infinite number of subsets. So you have a sequence of sets, or in probability theory, if we assume these are events, then you have a sequence of events, right? Now, this is a notation. This is another notation. What is the definition? You can no longer define this notation like this because you have infinite terms, right? You cannot just say dot, dot, dot. So here we use this representation or equivalent definitions of finite union and generalize them to define countable union and countable intersections. And you see the only difference just for all n in the set of natural numbers. So here, this set is replaced by a countable set n. And here, this finite set, countably finite set, is replaced by the countably infinite set. So here, suppose you have sequence of events or sequence of subsets A1 to A infinity. Actually, there is no infinity, A1, A2, dot, dot, dot. Then countable union means that at least one member exists such that your X is the member of that subset. Here, for all subsets, your X, your candidate X, must be a member. Got it? So far, so good. So these are finite. So finite union and intersection. You have countable union and intersection. And there is something more confusing: uncountable union and uncountable intersection. So uncountable union and intersection. What is that? It's like this. You take the union of some A sub alpha. So your subset A sub alpha is parameterized by some variable alpha. And here, alpha is a member of some index set where I is an uncountable set. And you may say, what? And here, for example, you have some beta in J, B sub beta, something like that. Here, J is also an uncountable set. In that case, this is the notation for the uncountable union, and this is the notation, becomes the notation for countable union. And you may find it interesting because if you restrict this index set as a countable set, countable infinite set, what's the difference between this and that one, right? If you restrict the index set to a finite set, then what's the difference between this notation and that one? So in some sense, these new notations successfully generalizes these previous notations. And to have a concrete idea, let me give you an example. Suppose you define A sub alpha as an interval from 0 to 1 minus, let me see. No, I don't want to do that. Just a second. Yeah. Be careful. Need to be careful. Yeah, something like that. Just alpha. I may define like this and index set alpha as, for example, 0 to 1. Okay. So alpha can be any real number between 0 and 1, 0, 1 inclusive. And for each alpha, you have a semi-open interval. Then let me ask you a question. What is this uncountably infinite union? What is that? You take 0, empty set, you take some epsilon positive, that is epsilon much greater than 1, then what do you have? A sub alpha is the interval from 0 to that, alpha excluding alpha. Now you increase alpha. What happens? Actually, the uncountable union is simply this interval, right? Am I right? Because alpha cannot be 1. Alpha can be 1, but A sub alpha cannot include 1. That is the precise statement. And similarly, you can define uncountable intersection. Got it? So this is kind of warm up. And now let's see something else. Here goes the definition. Given a sequence of subsets or a sequence of events, sometimes we have a very special sequence of sets or events that is similar to monotonically increasing sequence of real numbers. For example, x sub n equals n. What do we have? If you plot the graph, what happens? X sub 1 is 1, x sub 2 is 2, 3, 4. So it's strictly increasing. Similar concept can be defined for sequence of subsets or sequence of events. Here, the first thing, an increasing sequence of subsets or events. What does that mean? With less index, with greater index, they have this inclusion property. So what does that mean? So you have some A sub 1 that is included by A sub 2, is included by A sub 3. So if you just draw a kind of Venn diagram, you will feel that kind of you have a increasing sequence of subsets, right? And let me ask you, what would be the countable intersection of increasing sequence? Countable intersection of increasing sequence. Am I right? Let me see. Something's wrong. Just a second. Yeah, it seems that I have made some mistake here. Okay, probably I have to ask. Yeah, this one here. Okay. So given an increasing sequence of subsets, what if you compute the countable union of increasing sequence? First, what will happen? What is that, by the way? So as you have done in your high school math, we usually truncate the upper limit. What happens? Then A1 is included by A2. So if you truncate at A sub n, you have A sub n, right? So given that, given an increasing sequence of events or subsets, right? Your union, countable union, truncated up to an equals what? What is that? A sub n, right? Because here is your A1, here is your A2, dot, dot, dot. And if you stop at the nth union, then you have this one, right? Now, what if you continue? What is that? What does that mean? Yeah. That means what? As we just defined, if X is a member of this set, then what? There exists some I such that there is I in the set of natural numbers, right? And when you have increasing sequence, you have some interesting property. Similarly, you can define a decreasing sequence. Again, you have interesting property. Okay? And here goes another thing. Lim sup or limit supremum and limit infimum over sequence of subsets or events. And some of you just even do not know what is the lim sup and limit over sequence of real numbers. So let me just quickly talk about it. So sequence xn of real numbers. So you have x1, x2, x3, dot, 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 countably infinite real numbers. And given a sequence in your high school, what do you do usually? You check the convergence, right? You may just say that, okay, this sequence X either converges or not. Sometimes if it does not converge, we say it diverges, but it should be very careful because diverge somehow gives us an idea of diverge to plus infinity or diverge to negative infinity, something like that. But precisely speaking, not convergent includes oscillation, right? So be careful. But anyway, so first, limit xn exists or limit xn does not exist. That is your high school version of the understanding of a sequence of real numbers, right? And you loved some convergent sequence. But given the set of all real sequences, what would be the set of convergent sequences? It would be very small, right? Smaller than this dot in that scale. But in our high school, it's like it fills up almost more than half of our problems, convergent sequence. The problem is that there are other sequences that does not converge but has very interesting property. So they define the notion of lim sup or lim inf over a sequence of real numbers. And in order to talk about that, the simplest way, because this is not a real analysis course and my memory is decaying fast, I will just simply talk about that. First, you need the notion of limit point, a limit point over sequence. So as I here say, a limit point. What does that mean? Given a sequence, there could be more than one limit point, or there could be no limit point. What is a limit point? It can be understood visually like this. Suppose you have a graph of a sequence. Means that for each index, you put circle or mark X, something like that. Sorry, not here. A limit point can be understood like this. Suppose I claim, given a sequence, some value A is a limit point. What does that mean? Let's say A is a limit point means that for every epsilon positive, okay, the number A is a limit point of xn if, because this is a definition, if for every epsilon positive, what? There exists countably infinite or infinite. In this case, we just count, right? And n range, n is a count, n is a member of natural number, so we can count. So this infinite means countably infinite, infinite number of n's such that xn minus a less than or equal to epsilon. What does this mean? It sounds very similar to the definition of the limit of a sequence. What's the difference? In the definition of the limit of a sequence, we wanted to find capital N of epsilon. And after capital N of epsilon, all errors, these errors, are all less than or equal to epsilon. But here, it is the restriction is removed, loosened. We just want something like this. You take plus minus epsilon. So this is 2 epsilon positive. And what you want is that you can find some infinitely many indices. That's all. Got it? So what about this? Here goes the simplest example. xn equals -1 n raised to the n. Question, is this sequence convergent? No, it oscillates, right? So it does not converge. Second question, 1 is a limit point of this sequence? Yes. Why? Because for every, whatever epsilon positive you take, for even number n, this is true, right? Third question, -1 is a limit point? Yes. Why? Because you can for every odd number, right? So every number of odd numbers are countably infinite. So they are infinite, right? So something like that. Now, it seems that if the sequence really has the limit must be what? The limit must be a limit point. Am I right? So this limit point somehow generalizes the notion of the limit of a sequence. If the limit of a sequence exists, then you must have what? You must have unique limit point, right? And the limit point equals the limit. What about there are 2 limit points, given a sequence? The sequence can never converge, right? So interestingly, this notion of a limit point opens up a new idea of viewing a sequence of real numbers. Unfortunately, in India, they teach this notion in high school math. In Korea, they do not. And every year, the coverage of high school math reduces. And we are doomed in that sense. That's what I believe. Okay, so whenever I have a chance, I tell students, if you have a high-ranked government officer in your relatives, please tell him or her, please stop reducing the coverage of high school math. Okay? We are far behind in other nations. Anyway, so this is interesting. Now, what if we have many limit points? Then we may define supremum of limit points because we have a set of limit points. We may define infimum of limit points, right? Then what can we say? What does that mean? We have many limit points. For example, here goes another example. Suppose xn equals sine n. What happens? It's not sine 2 pi n, okay? xn equals sine n. Let me ask you a question. Is value 1 a limit point of this sequence? You somehow know it's true, right? You cannot just prove, but okay, let me draw sine x, right? And I sample at every integer, and it seems that whatever epsilon positive I take, I will eventually find countably infinite number of n's that is within the 2 epsilon bound from 1. So 1 is a limit point. What about -1? In the same reason, -1 is a limit point. What about any real number between 1 and -1? It is also a limit point. What? So in this sequence, the set of limit points includes all the real numbers between -1 and +1, including the endpoints. Given that set, what is the supremum of the limit points? 1. What is the infimum of the limit points? -1. Got it? But that is actually a little bit different from the lim-sup and lim-inf. Lim-sup and lim-inf means more than that. Okay? It's not just the supremum of limit points or infimum of limit points. This is very strangely defined. That's what I'm going to say. So before I talk about lim-sup and lim-inf of the sequence of subsets, here let me define the lim-sup and lim-inf of a sequence of real numbers. And interestingly, the definition is very similar. So here, so this is the notation, lim-sup of xn. It's not limit of xn, okay? This is lim-sup of xn. How do we define? And lim-inf of it's similar to the, as I told you, it's similar to the supremum of the limit points, but it's a little bit different. So what we do is, if I remember correctly, what we do is this. What about supremum of m greater than or equal to n, xm plus 1, xm plus 2, So it's not the definition yet. Let's consider a truncated sequence. So you truncate your entire sequence from xm to infinity, x infinity. So you truncate the first, let me put 1 here, okay? First m terms, okay? Then what do you have? You can find the supremum of this set. Right? Supremum of this set. You can interpret the supremum as maximum, but maximum may not exist in some cases. However, supremum exists, right? You know what does that mean by supremum? Least upper bound. Okay? And what is this one, by the way? If you view this as something parameterized by m, it's a sequence. You can define this as a new sequence, y sub n, right? What's the property of the sequence y sub m? Let's see. Let's consider y sub 1. What is that? Supremum of the entire terms in the sequence, right? So you have some number. Now you remove first thing and consider y sub 1. Then you have y sub 1. It's not good. Let me go back to my previous. Okay, 1. Okay, this would be better. Okay. Okay. So y sub 1 means that the supremum of all the terms. Y sub 2 means that supremum of all the terms except the first term. What happens? You take 1 by 1. So this y sub m sequence is decreasing. Y sub m is a decreasing sequence, right? Now you consider the limit of this sequence. And here goes a very interesting theorem or lemma from the analysis. You have a monotone increasing sequence of real numbers. It either converges or diverges to infinity. It can never oscillate. Monotone increasing, right? If it is bounded, it always converges. You don't need to find the limit. If it is bounded and monotone increasing, it always converges. Similarly, if you have a monotone decreasing sequence, and it either converges or diverges to negative infinity. If it is lower bounded, definitely it converges. Got it? So this limit of y sub m either diverges to negative infinity or converges. Right? And another one is this lim inf. You can also consider some z sub m that is defined as infimum of xm plus 1, xm plus 2, Then similarly, you can easily show that this sequence monotonically increases. And now you consider the limit of it because it's strictly increasing sequence. And what about the relation between lim sup and sup of n? Definitely, this is greater than or equal to lim sup, right? And what about infimum? You have this relation. Then what about the relation between these two? In order to see that, let's just compare the mth element of ym and mth element of zm. So you have the same set. You take the supremum and you take the infimum. So for each element, you have what? You have z sub m less than or equal to y sub m. Now you take the limit. If the limit exists, then what happens? If the limit exists, what happens? You have limit of this less than or equal to that one, right? So in general, what you have is some property like this. Inf of a sequence is less than or equal to lim inf, less than or equal to lim sup, less than or equal to sup. Something like that. And what about the sequence is convergent? What if sequence converging? Interesting thing is that if sequence converges, these two are the same. So you take the lim sup, you take the lim inf. If they are equal, that is the limit, something like that. Let me see. Let's see. Yeah, something's missing. Just a second. Where is inf, by the way? Yeah, just a second. I believe I forgot something. Just a second. Wikipedia, I need to see. Yeah, it seems that my memory deteriorates every time. Yeah, there is something missing here. Lim sup. Okay. It's a shame that I forgot this. And I'm not sure the definition. Okay. Definition. Lim sup of a set. Lim sup of sequence. Okay. Okay. Yeah, it seems I'm correct. Yeah. Okay, I'm correct. 큰일이에요, 그렇죠? Okay, anyway, this is a sequence. Given a sequence, you not only can define the limit, now you can define the lim sup and the lim inf, which generalizes the concept of the limit. Okay? Sometimes a sequence that does not converge has a very good lim sup and lim inf. And they may be very close, even though they are different. Then what can you say? What can you say? You can say actually a lot, and that's what I'm going to say. And here goes the definition of lim sup and lim inf of a sequence of sets, and that will give you what do we expect for a kind of brother and sister definition here. And here goes a very similar notation, but completely different one. See, here we have a sequence of what? Sequence of subsets or events. Now we define the lim sup of A sub n. And here we have, what is this one? Countable intersection. And this is countable union. So union runs from n to infinity. Right? And you have A sub m. And when I first saw this definition, I was frustrated. Actually, we need some parentheses here, which makes this definition very easy to understand. Now, what is this one? This is very similar to that one, except we have union of sets. Here, we take the supremum of infinite numbers, right? Here, we take the union of subsets. What is that? You have, let's define this as B sub m. And what is that? That is A sub n, let me see, union A sub n plus 1 union A sub n plus 2, something like that, right? Because your index m runs from n to infinity. So you have n plus 1, n plus 2, something like that. And here goes something similar. What if we choose m equals 1? Then this is A1 union, A2 union, A3 union. So it's the biggest union given sequence of subsets, right? Now you take B sub 1. What does that mean? You now take the union from A sub 2, A sub 3. So the union may be a little bit smaller, right? So you can say that B sub m sequence is a decreasing sequence of events, right? So B sub m decreases. What about lim inf? Here you have C sub m, that is A sub n intersection A sub n plus 1 intersection A sub n plus 2, even though this is not a precisely mathematical expression, this is more appealing to our feeling, right? And what happens? C sub m increases because if you have m equals 1, every A sub i's are intersected, right? Now, if you choose m equals 2, then excluding A1 for A2, you intersect. So this intersection increases. That is very similar to this situation, right? So there is a parallelism between the lim sup and lim inf of a sequence of real numbers and lim sup and lim inf of a sequence of events or sequence of subsets. Now, instead of taking the limit, you take the intersection. What does that mean? As I told you already, this is a decreasing sequence. Now, given the decreasing sequence, you take the intersection. What does that mean? So you have B sub 1, you have B sub 2, and you have B sub 3, and you intersect all of them. Then, as I told you before, if you truncate the intersection, what happens? You have, again, smaller and smaller sets, right? from the biggest set. So what you eventually have is this one. So you have intersection of all A sub i's. That is the subset of lim inf of, let me use n. This is a subset of lim sup of A sub n, and that is the countable union of the events. Okay, so this is the kind of relation between countable intersection of a sequence of events, countable union of sequence events, and lim sup and lim inf of the sequence of events. And of course, if lim sup and lim inf are the same sets, then what do we want to claim? The sequence of subsets converges to a subset. Okay, so you may say that, okay, I may define a sequence of subsets. I may define limit A sub n. Actually, we don't do this, because that is very strange definition. It's not a sequence of real numbers. So what we do is this, as I just told you, we start from the sequence of real numbers, and we somehow redefine the limit of a sequence as what? As the case where lim sup of the sequence and the lim inf of the sequence are the same. Now, similarly, we define the notion of the limit of a sequence of subsets. How? We define the lim sup of a sequence of events and lim inf of the sequence of events. If they are the same, we call now that as the limit of a sequence of events. Got it? So by doing that, we have a very parallel results in the sequence of real numbers and sequence of subsets. Okay, I believe we are almost ready. Yeah, to talk about the examples. Okay, now let's see. So given a sequence of subsets or events, if you want, in this case, no probability, so it's a sequence. Now, show that lim sup of A sub n is Q plus. Here, Q plus is all non-negative rational numbers. And also, show that lim inf of this sequence of subsets of real numbers, is what? Z plus, which is the non-negative integers. You think, and you can easily show that actually. Now, let me ask you, is this sequence has the limit? Your answer is no, because they are different sets, right? So you have just seen non-convergent sequence of subsets of real numbers. Now, the second question. You have some sequence of subsets of real numbers, B sub n, that is closed interval, 0 to n over n plus 1. Now, what is B sub 1? From 0 to half. What about B sub 2? From 0 to 2/3. B third, 3/4. 4/5. So this sequence increases, right? And you have an increasing sequence of subsets of real numbers. Then what happens? And similarly, you can show that it either converges or not. But anyway, in this case, this is bounded and it really converges. And here, you can show that lim sup of this sequence is a semi-open interval, 0 to 1. Lim inf is also the same. What does that mean? This sequence of intervals actually is a convergent sequence of intervals. And the limit is 0 inclusive, 1 exclusive. Got it? So you have seen some definitions and 2 examples. Given that, let me skip this one. Where is the Borel-Cantal lemma? Okay. Yeah. Here goes the first Borel-Cantal lemma. Now you are ready to read the Borel-Cantal lemma. Okay. And here, the lemma states that under certain conditions, an event will have probability either 0 or 1. By the way, an event having probability 1 is very good to us because that is related to what? Almost sure something, right? Or with probability 1 confirmation. And as I told you, the Borel-Cantal lemma is quite often used to prove what? The convergence of a random variable to another random variable almost surely. So you have some idea. Okay. And accordingly, it is best known as a class of similar theorems known as 0-1 laws. And other examples include Kolmogorov 0-1 law, blah, blah, blah. And here goes the first Borel-Cantal lemma. Let E1, E2, dot, dot, dot be a sequence of events. Now you understand what is a sequence of subsets of real numbers, and also you have a vague idea of a sequence of events, right? No problem. And given a sequence of events, and then the Borel-Cantal lemma says that if, okay, so this is a lemma, okay, not definition. If probability of each event, what is this one? It's a number, right? You can just say that this as some p sub n, and that is always less than or equal to 1 and greater than equal to 0 because it's probability, right, of an event. Now you sum up these numbers, countably infinite numbers, and that is well defined because these are non-negative reals, and that is finite. If this condition holds, so if this is true for a sequence of events, then this is interesting. Don't read this. This is too difficult. Then you have this. Then you have lim sup of the events. And you know that lim inf of a sequence of subsets or lim sup of a sequence of subsets are subsets of, in this case, the event space, right? So it's a set. And the probability of that set, that event, is 0. What does that mean? Probability of the complement of this set. Probability of the complement of this set is 1. What does that mean? You have almost sure something. With probability 1, you can state something, blah, blah, blah. Okay. And here it says infinitely many, and sometimes of finite many, sometimes all but finitely many. That confuses you a lot. But you think about that part, not here today. Okay. What is important is this one. Now you have successfully extended the notion of a sequence convergent, non-convergent of sequence of real numbers, where lim sup and lim inf are defined, to what? Sequence of events, where lim sup of the events and lim inf of the events are defined. Now, the Borel-Cantal lemma is about to prove some limiting event has probability 1. And that limiting events involves the notion of lim sup of the events. Got it? So that is kind of what I planned to convey to you, because this entire, how to say, major theoretic probability theory is too huge. As I told you, when I was at your age, a graduate student, the trend, of course, that trend was dying out, but trend in graduate research was to mathematically prove something. So professors urged their PhD students to take, or master students take the real analysis, major theoretic probability theory courses. And we were tortured to prove something and taking courses with math PhD students. You don't need to do that. These days, many of the students are far from that kind of research. However, sometimes you need to read and understand what something means in very important reference of your research. If you don't have this knowledge, just nothing you can understand. However, if you have some notion of the convergence of a sequence of random variables, and you have some idea of the convergence of a sequence of events or subsets, you can far better understand the meaning of the theorem or paper or some results. That's why in this graduate level probability course, I have spent a lot of hours to explain the difference between convergence, almost sure sense, difference and convergence in probability, convergence in distribution, something like that. Okay, so please remember this. Borel-Cantalli lemma is one powerful tool. I'm not saying that it's omnipowerful or omnipresent tool. It's a powerful tool to prove almost sure convergence. Okay, let me skip all other things. Okay, here goes some. If you take the complementation, suddenly it becomes the lim info of the complement of sequence, but that's not important at this point. Of course, there is a so-called second Borel-Cantalli lemma, and which is more complicated to understand at this point, but I will leave it for your future research. Anyway, some very simple problems actually requires to use Borel-Cantalli lemma to prove a very simple result. And if you have interested in that, please read it. Let me skip it. Okay, so I believe I'm almost done. Okay, so here goes the Monte Carlo simulation, especially Monte Carlo integration. And some of you already know what I'm going to talk about. So suppose in your mathematical analysis, you confronted to have some integral to be evaluated. And this integration is, for simplicity, is limited to the finite interval 0, 1. And you have a function g, and integration variable is x. What do you do if you are given to find out the value of I? If function g is very simple, then probably you integrate yourself. For example, gx is x. You can even just compute in your brain. Gx is the sum polynomial, no problem. Gx includes some elementary functions, still no problem. You can use Mathematica or something, symbolic computation in MATLAB. They give you the answer. But sometimes function g of x is not given explicitly. It is obtained by some probabilistic computation, very complicated. Then what do we do? Or gx is very, how to say that? Easy to evaluate at each x. However, there is no closed form. Okay. So here you have some box that gives you the value of output whenever you put an input. However, there is no explicit formula. Then how can you integrate? Right? Hyunjung probably have seen something similar. Suppose that is a neural net, and you put some complex number, and you have some output. And you have trained that model by using some input-output pair, but you don't know whether what is exactly inside. For example, that is enclosed in a box. You cannot see the individual coefficient. And you are asked to compute integral. What do you do? In this case, the strange reformulation of this one is tricky. Suppose x is uniform on this interval. Then the value I is what? Nothing but This one. Why? Because the expectation of a function of random variable due to the fundamental theorem of expectation is integral of g of some variable times the PDF, if it exists, of that random quantity, dx. And here, what is it? X is uniform. So this is 1. And you have g of x dx. Okay, so this is the first trick. But still, it does not give us any idea about how to evaluate. However, we've learned what? The law of large numbers. So we know this, not just a single one. Let's generate sequence of random variables. And that's not difficult. As far as you can use some random number generator. And whenever you push the button, it generates independently. And it takes the sample from some uniform 0, 1 distribution. And what can you do? From the law of large numbers, expectation of g of x is what? Can be the limit of the arithmetic average of g of x1 plus g of x2 plus ... up to g of xn. Or let me use lowercase. Right? That is law of large numbers. Of course, in order to apply a specific law of large numbers, we need to find out whether g of x has a finite mean or variance, right? Because some different versions of laws of large numbers has different conditions. Some law of large number requires finiteness of the variance. Some law of large numbers even does not require independence. Some simple, very simple law of large numbers requires IIDness and finite mean exists and finite variance exists, something like that. And then we apply. What does that mean? So in order to find this value I, you can just take sufficiently large n and compute the arithmetic mean. That is usually this type of idea called Monte Carlo integration. You compute the integral, but you introduce some random number generators and rely on law of large numbers to approximate the value. Okay? And you may say that, oh, I may not be needing this Monte Carlo integration. Actually, whenever you compute probability of something, for example, probability of bit error, probability of symbol error, probability of packet error, the outage probability. Every probability is what? As once I told you, probability of something can always be written as expectation of the indicator function of something, right? So the indicator function always, there exists some indicator function that can be used to convert the probability of something to expectation of something. What does that mean? Expectation of something is always what? Integral of variable times probability measure d omega, something like that, or ds. That is integral, okay? So whenever you compute the probability of something, you may use, I'm not saying that you have to, you may use Monte Carlo integration. Got it? So please remember this. Okay. Okay. Let me skip because we have a lot to say. Okay, this part I've done. Yeah. So let me quickly give you the summary of what we learned. Okay. So we learned 4 modes or 4 definitions of the convergence of a sequence of random variables. First, almost sure convergence. Second, convergence in piece mean. Third, convergence in probability. Fourth, the convergence in distribution. And even though in previous slides, I have written these definitions a little bit differently, here I have rewritten to make them look very simple, similar. Just xn converges to x almost surely. In the piece mean, in probability, in distribution. What's the difference? They all involve probability. Even though this apparently does not, but expectation is always what? Summation of value times probability. So we have probability, 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 and probability. Because this characteristic function or CDF is also probability of something. And almost sure does not have what? Something outside. Just probability equals 1, right? And even the limit is inside this argument, right? Similar definition is in probability, where the limit is outside the probability. So actually, you have a sequence of probabilities. For each epsilon positive, you have a sequence. So you have how many? Uncountably infinite sequence converges to 0. So they are different. In the piece mean, it's very simple because you use expectation. What about the distribution? You don't even think about probability, the event. You just, so you don't consider some set of S such that blah, blah, blah. You just compute the limit of the CDF or limit of the characteristic function. And you check whether it converges to the CDF or characteristic function of your limit. And the remark is very simple. In many cases, I do not say, but in many cases in engineering problem, you need convergence in distribution. Of course, you specifically may need convergence almost everywhere or almost surely. However, if what you need is this one, you may prove a stronger result, or a stronger result. It doesn't matter. Got it? And I gave you some idea. To prove this one, sometimes you use, not always, you use the Borel-Cantor lemma that involves the idea of lim sup and lim inf of a sequence of events, which is different, but similar to the notions of the lim inf and lim sup of a sequence of real numbers. And you have some idea. You cannot 100% understand after a single class meeting of a even in the graduate electrical engineering course. However, I believe you understood a lot compared to what you just entered this classroom. Okay, so I haven't yet started this part, but I will do this Thursday. So we are going to use, be careful, we are going to use this convergence idea to talk about continuity, differentiation, and integration of random processes. Okay, this is the core of stochastic calculus, which is also the core of financial statistics, actually. So, for example, if you go to the library, take arbitrary textbook related to the mathematical finance, you will see this topic, stochastic calculus. Okay, I believe I motivated enough. That's all for the day.